Hi, welcome back to Introductory Statistics. We're going to talk about the law of averages in this week. We'll cover chapter 16 from our textbook. So suppose I have a coin and I want to toss it. I want to measure the number of heads that I get. And so if I were to do this experiment and repeat it many times, here's an example where we have a simulation from a computer that just randomly toss a coin and record the number of heads. So for example, on the left, there's actually two columns of data, where on the first column, on the first set of columns, we have the number of tosses, the number of heads for those tosses, and then the difference between the number of heads and half of the number of tosses. So for example, if I toss the coin 10 times, half of the number of tosses is 5, and say in this example the number of heads that showed up was 4, so 4 minus 5 is -1. And look at another example in the simulation where the coin was tossed 100 times. Half of that is 50, but the number of heads that showed up was actually 44, so 44 minus 50 is -6. And so as I go up, for example at 6,000, the number of heads that showed up was 3,009, but the number of heads that we expect is half, which is 3,000, so that difference is 9. So we noticed that for the most part, it seems like the number of heads that showed up was about 50%, or half of the number of tosses. And the difference, notice as I go up, the difference kind of, the numbers get a little bit bigger, but really when you compare to the number of tosses, that difference is still a very small number. So really we do have about 50% of the time that we get heads. So here's some terminology. We want to talk about something called the chance error in the number of heads. So suppose I suppose I toss a coin and we have the half of the number of tosses. We compare half the number of tosses and the number of heads that we actually get, and then really that difference is called the chance error. In other words, half the number of tosses plus the chance error is what you observe as the number of heads. And so this error is likely to be large in absolute terms, in the sense that if I do a lot of tosses, I expect this error to be big, but that number should be small relative to the number of tosses. And so this is the law of averages. And so stated differently, the law of averages can be stated in terms of percentage terms. With a large number of tosses, the percentage of heads is likely to be around 50%, although it won't be exactly. And so another way to think about this is that as I have more and more tosses, then the chance error expressed as a percentage should go down to 0. And so for example, if I were to do 1,000 tosses, then this chance error is as a percentage, it should be very close to 0. So let's go back to that table again and explain. So for example, if I was to toss 10,000 times, I get 5,067 heads, say in one simulation. And notice that difference between the number of heads and half of the number of tosses is 67. 67 is a big number, but compared to 10,000 toss, that's a small number. So that means that this error, this chance error, is close to 0 as a percent, because if I divide 67 by 10,000, that's essentially 0. Okay, so let's do an example. Suppose I have a box of tickets, and these tickets are numbers from 1 to 6. And we're going to draw 25 tickets with the replacement. So I draw a ticket, I put it back, and I add up the tickets. So here's an example. I do this 25 times. Here are my numbers. And then again, we're doing this with replacement. So I add these up, add up all the 25 tickets, I get 88. Now suppose I do this experiment one more time. Actually 10 more times. And so each time I draw 25 times, I add up all the tickets. So the first time I got 88, the sum of 25 tickets. The next time I do this, I get 84. Again, the sum of 25 tickets. I keep doing this, and I get the following numbers. And notice that we want to understand chance variability, meaning that when I do this many times, these numbers, do they vary a lot or do they vary a little? How do we measure that variability? So the first sum is 88, and then it goes down to 84, goes up to, go down to 80, and then it gets as high as 95. So let's look at these numbers, try to understand a little bit better. So for example, what is the smallest possible sum? So again, I'm picking tickets from this list. So I picked 25 tickets. I mean, the smallest possible case is when if I pick a 1 25 times. So that's in theory, it could happen. I could get 25 times, where each time is the one ticket. So the smallest possible sum is 25. That means that I get 25 tickets, all of them are ones. The biggest possible sum is I get 25 tickets and all of them are sixes. So that's 150. So the smallest possible sum is 25. The biggest possible sum is 150. So that's quite a big range from 25 to 150. But notice when I do this experiment 10 times, again, this is done by computer, I actually get numbers that they don't vary too much. Again, we don't get anything that's really close to 25, and we don't get anything that's even close to 150. So that says that it's very unlikely to get a lot of ones, and it's also very unlikely to get a lot of sixes. And so we get somewhere kind of in the middle. And so in fact, that the numbers we observe is from 75 to 100. So the question here is that we want to understand this problem in the sense that we want to know what's the chance of the sum turn out to be between 75 and 100, and so why is it that we don't get numbers that in kind of the extreme range? Okay, the object of so let's talk about something called the box model. This will help us understand many kind of problems and help us kind of simplify a problem into something mathematical and very basic rather than all the bells and whistles of the actual problem. And so in the box model, when we look at a problem, we want to figure out what kind of numbers can come up, whether it's in a game or some kind of a something at the casino. What kind of possible answer can we get, and then how many of each kind, and also how many times are we playing the game, how many draws are we making. And the purpose of the box model is to analyze chance variability, and we want to kind of simplify it so that we can get a simple box model to explain maybe a game that might be complex. So for example, let's look at the roulette game. So this game has a lot of, like I said, a lot of bells and whistles. You have this huge wheel that has 38 pockets. One of them is number 0, another is number 00. The rest are number from 1 to 36. And then we spin the wheel, and the ball is thrown into the wheel, and the ball bounces around. And it's like the ball is equally likely to land in any of the 38 pockets. Before it lands, bets can be placed on the table. One possible bet is that we either bet on color, red or black. Now 0 and 00 is actually color green. So 2 of them is color green, and then 18 of them is color red, 18 is color black. Now if you bet $1 on red, say, and then red comes up, then you take your $1 back and you win $1. Otherwise you lose that $1. If you get you pick red but black shows up or green shows up, then you lose that $1. So let's kind of understand this problem. Again, this problem seems to us a lot of details here. The colors, the wheel, the numbers, right? A lot of things that seems complex. And so when we look at a problem like this, we want to ask some questions about it. We like to kind of boil it down to a simple box model. So in a box model, we just want to know whether we win $1 or lose $1. We don't care about all the different colors, the numbers, a lot of those details are irrelevant. Depends on the game. And so when we play this game, either we win $1 or lose $1. And so that's the first thing. So that means either when we pick a random ticket, for example, out of this, if we convert this into a box model where the box contains a bunch of tickets, the only 2 possible tickets you can get is either a +1 to win $1 or -1. So that's kind of the boxes represent a simple version of this game. The second question is that in this box, how many of each kind do we get? How many times can we get a +1? How many times can we get a -1? Well, if you pick a color, then we have 18 of them are red, 18 of them are black. And so you win if you get the one of the 18, and you lose if you get either black or green. So the casino has an advantage of the 2 green tickets that could help them win. So the chance of winning is 18 out of 38, and the chance of losing is 20 out of 38. Again, 18 of the tickets, 18 red, I can win $1, but the 20 tickets, if I get any of the 18 black or 2 of the green, I lose $1. So basically boiled the problem down to a simple box model with only 2 kinds of ticket, +1 and -1. The +1, there's 18 chances of getting a +1. The -1, I have 20 chance of getting that. So that's kind of the purpose of the box model, to simplify it into a simple box with a certain number of tickets, how many of each. And now if we want to play this game, we simply reach our hand in, pick out a ticket, and then whatever ticket we get is basically what happens to the game. Of course, this box model is a very boring game, right? We wouldn't go to a casino to pick a ticket out of the box, but it's kind of a simplified version of this game. You know, when you go to the casino, you like to see all the colors and all the bell and whistle that comes with the casino. But we kind of strip that away and keep it simple, but convert that problem into a box model. So we play one game, we pick a ticket from this box. But we play many games, that means that every time we play, we pick the ticket from the box, then we replace it, and we do it again, over and over again. And so suppose that we play this game 10 times, and we bet $1 on red each time. And then something that we can compute is called the net gain. The net gain is positive if you head at a certain point in the game. The net gain is negative if you are behind at a certain point. So let's do an example. Let's see if we can do an example here. Okay, so let's just say that we play 10 times and we get the following: red, 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 black, green, red, red, black, black, red. So R is red, B is black, and G is green. The green is for the numbers 0 and 0, 0. So in table 2, we're gonna show you the net gain. So if I get red, I win $1. That's the first game. So my net gain is $1. If I get a red again, I won again. So I get another $1. So my net gain is $2. If I get another red, I win another $1. So my net gain right now is $3. So at this point, after 3 games, my net gain is +3. That means I'm ahead $3. If I get a black, then that means I lost $1 in the next game. So now my net gain is now 2, because if I add up all my win-lose, I get a +2. So you can see how this work. Either +1 or -1, and my net gain tells me where I am currently at this point in the game. So for example, at this position over here, my net gain is 2. That means that so far, right, if I look at all the winning and losing, right now I'm ahead $2. Okay, so let's look at so you bet $1 on a single number at the roulette, and let's look at a different game now. So now this time, let's say we're not betting on colors, but we're betting on, say, the number. And if I bet on a number and I bet $1, if I get the right number, I win $35. But if I don't get it, then I lose the $1. So this says that a gambler say that this single number this single game pays 35 to 1. Suppose we play the roulette 100 times, betting $1 on the number 17 each time. So you want to figure out the net gain. So the net gain is like the sum of blank draws made at random with replacement from the box blank. We're going to fill in the blanks. Okay, let's figure out this box model. What numbers go into this box? Again, we want to simplify this problem. So if we have so again, there's only 2 kind of tickets. If I win the game, I get $35. So one ticket is 35 plus $35. But if I lose the game, then I lose $1. So there's only 2 kind of tickets, either +35 or -1. Now we want to figure out how many of each of these tickets can we get from this box. We want to convert this into a box model. Well, because of the numbers, remember the numbers go from 1 to 36, and then 0, and then 0, 0. So that means if I get, but there's only one ticket that gives me a winning $35. That ticket is 17. Okay, and we're betting on 17 each time. There's only one ticket that gives you, if you're betting on a number, there's only one ticket that will give you $35. Every other ticket means that you pick the wrong ticket and you lose $1. So it's 37 tickets is -1. One ticket is $35. Now, so if we were to play this game 100 times, then that's essentially picking out 100 tickets at random from this box with replacement. Because each time we played the game, we had to put back all the tickets. So that's basically the box model for this game. Again, having the box model allows us to kind of simplify this problem, which seems kind of confusing, into something that we can understand very simply. That you have a box of a certain number of tickets. Playing this game is like picking a ticket from this box at random and replacing it if we want to replay the game. Okay, so let's look at we want to understand in the next chapter something called the expected value, and also something called the standard error. So we play this game at a certain number of times. We expect to win or lose a certain amount of money, and then we want to know, well, what is the variability to this game, and so, for example, imagine generating a number through the following chance. I toss a coin, and I do it 100 times. I'm gonna get 57 heads, and 7. That means 7 is above. The expected value is 50 because I expect to get 50. But if I get 57, then that means that this is a little bit off from 50. I get 7 more than I expect, so the chance error is 7 plus 7. If I do this again and this time I get 46, that means I have a little bit less than what I expect. Again, I expect half, which is 50, so the chance error is -4. If I do this again and say I get 47, then the chance error is -3. So the idea here is that we expect a certain number, which is 50, but we might not always get 50. There's always this chance error, and so we want to kind of measure this chance error, and so that's called the standard error. We want to figure out if I were to do this experiment many times, I want to measure the kind of error that we might get. So we call that the standard error. And so in the next chapter, we'll talk more about expected value and how to measure this standard error. Again, a lot of the games that we talk about, a lot of the experiment we have, there's always a chance. Even polling, like when we conduct polls, there's always chance always comes in, because we have to randomly pick people to ask them who they would vote for. We can't ask the whole country, so we have to do these polls, and we have to kind of rely on chance to select random people to poll. And so so chance error comes up a lot, and we want to be able to understand that error and understand how to measure it, so that we know that there's some chance involved, and we can measure the kind of errors that we get, and that way we can kind of bound our result based on that error. Okay, next week we'll talk more about this. Thank you.